I will mention, some of you may know that the original pair source work was actually conducted with Huan Chen. We worked closely in the lab together. So if you'd like to hear any stories about Huan Chen earlier in her career, you can talk to me. And if you'd like to hear stories about me earlier in my career, you can talk to Huan Chen. Yeah, it's wonderful to be here. I've had a really fantastic time talking to many of you about science. Lots of really fun, creative science that I've seen today, hoping to have more conversations the rest of today and tomorrow. I'm going to tell you about science that's ongoing in my group and in collaboration with Dave Schuster's group, exploring cavity quantum science. I would say that in some ways, the motivating central theme of my science, everybody has a hammer and is looking for nails in some way. And the hammer that my group likes to bring to bear is exotic types of resonators. So one of our two main foci is sort of condensed matter kinds of physics experiments using cavities. So on the cold atom side, this includes things like making fluids of optical photons, where the geometry of an optical cavity can make the photons act like they're in magnetic fields, make them act like they're trapped. And then we can add Rydberg atoms to make the photons interact with each other. On the microwave side, we trap photons in arrays of superconducting qubits and treat that as sort of a synthetic lattice material where the photons can collide. And then we have another sort of half of the effort that focuses on more quantum information kinds of applications, things like performing transduction between optical and millimeter wave photons using atoms, and a new experiment where we can make resonators with sort of sub-micron mode wastes, go into the strong coupling regime for individual atoms, and even make arrays of these resonators spaced by a couple of microns for either quantum computing, quantum communication, these kinds of things. So the main focus for today, though, is going to be on making fluids and solids of microwave photons using superconducting circuits. And then, time permitting at the end, I'll talk a little bit about working towards interfacing these superconducting devices with optical photons using atoms, and then just transduction in general and how that can connect to atom pairs. So let's just hop in. And when I say a material, I think of this as a collection of particles that interact with one another and thereby sort of organize or order. So there are a couple of ingredients that one needs to make this happen. And the analogy I'd like to share is just starting with this simple simulation. Each of these blue dots is a particle that at large distances is attracted to each other dot. And as it gets close to that dot, it gets repelled, okay? And the only other ingredient I've added is a little bit of friction. So it's worth it to take 5 seconds and guess what's going to happen when I turn on the dynamics here. So as you could probably have guessed, these particles order into a lattice. I didn't tell it a priori that this should be a triangular lattice. All I did was provide the ingredients for the individual particles. You can see we have a lattice, you can see phonons, you can see all of that physics just from these simple constituents. So what are the constituents that we need? We need a collection of particles, that is to say, objects that respond to forces in some sane way. Okay, I need interactions between the particles, that is to say, a distance-dependent energy. And then I need some way to help this system organize or order. So what do I mean by a way to help the system organize or order? Well, I need some way to get it into a low entropy state, to suck entropy out of the system. So let's go through what each of those things means in terms of Hamiltonian engineering. And then we can start to think about how one might do this with photons. So imagine I have a massive particle, like an electron. It's going to be moving to the right, and I'm going to apply a force on it to the left. What happens is it slows down and turns around and goes in the other direction. What happens if I repeat this experiment with a photon that's moving to the right? I apply a force on it to the left, this changes color, right? Well, that's not really what a particle does, right? So this kind of makes you think maybe a photon's not a good constituent of a material. So, but why does this happen? Well, the reason why it happens at some level is that the dispersion relation for light is linear. And so that is to say the relationship between the momentum of the photon and its energy is linear. Because when I apply a force to the photon, what I do is I change the momentum, right? Momentum is decreasing. But the problem is that the velocity of the particle, the group velocity, is the slope of the line, and it doesn't depend on the momentum, right? So I apply this force, I change the energy of the photon, I change its color, but I don't change the speed with which it's moving. But this immediately tells us what we need to do. We need to trap the light in some kind of a material, right, that changes the dispersion of the photons such that when I apply forces to them that change their momentum, it also changes their velocity. So this could be an array of cavities. It could be one cavity with multiple transverse modes, but that's the essential idea. I need to change the dispersion of the light. So that's challenge number one. What's challenge number two? Well, imagine I have two electrons that come towards each other. That's 21st century CGI for you. We can get a collision between them. Particles bounce off of each other. What if I repeat this experiment with photons? Well, if I have a photon that's moving to the right, that's a solution to my Maxwell equation. If I have a photon that's moving to the left, that's a solution to my Maxwell equation. If I have a photon moving to the right and a photon moving to the left, that's also a solution to my Maxwell equation. It just moves straight through each other, right? We don't live in the Star Wars universe. These photons collide. But we might ask, well, how do electrons collide? Well, electrons collide by exchanging a virtual photon, right? That's the lowest order Feynman diagram that gives us collisions between electrons. So maybe we could do the same thing with photons. Maybe we could have them exchange a virtual electron to collide with each other. Would that work? Well, it turns out that Feynman diagram is disallowed by all of the symmetries. If you name a symmetry, it's disallowed by it. But this idea is kind of the right idea. I can instead have some higher order Feynman diagram where I exchange several photons. Well, it turns out this Feynman diagram is quite small, right? But fundamentally, the idea is to mediate the interactions between photons using matter, much as we mediate the interaction between electrons using light, okay? So we've got the idea of the first two ingredients. We're going to make our photons respond to forces in sane ways by trapping them in some material that gives them a more favorable dispersion. Literally any dispersion is more favorable than linear, okay? And then we're going to make the photons interact with each other via their interaction with that material. Okay, so the last question is, why do I need some kind of entropy management? Well, what if I had these photons, I just prepared them here, and I let the system evolve without any friction? Well, this is like undergraduates when you put out cookies, right? You've probably seen this. Maybe in Singapore, y'all are better behaved, but that's the experience we had in the US, right? The point is, if you prepare a high entropy state, if you prepare an arbitrary initial state, you just stay in that high energy state. And if you add friction in a sort of generic way, well, then you're going to cool your system down, but you're continuously measuring it via the friction, right? And so you'll end up in a classical state at the end of the day where you've sort of projected out all of the entanglement. So we have to have some kind of way, either by careful cooling or by some other technique for entropy control, to build interesting many-body states. So that's the shape of the problem. And what I would like to suggest is that as I go through this story, you think about it in the context of how are we making the individual photons act like particles with mass, with sensible dispersion? How are we making them interact with each other, and how are we sucking entropy out of the system? How are we preparing low entropy, strongly interacting, strongly entangled many-body states? So, and this story will sort of be broken into three parts. First, I'll tell you how to prepare solids of light. Then I'll tell you how to prepare fluids of light. And then I'll tell you how to prepare like Schrodinger cat states, superpositions of many body states of the light, and how to detect that we're actually in these macroscopic superposition states. So at some level, this story starts to bridge the gap towards thinking about a quantum matter platform in the language of quantum information. Okay, so the first thing we need to do if we want our photons to act like particles in a material is we need to have a lattice site that our photon lives in. Much as an electron lives on one ion in the material and then can hop from one to another, we need to be able to have the individual lattice site to start with. So what makes a good lattice site for microwave photons is an LC oscillator. In a normal LC oscillator, there are lines at the top and bottom here. I don't know where those went. They're usually there. If your LC oscillator doesn't have those lines, well, then you've added some extra series capacitance there, and that's not what we're going for. But anyway, this is some LC circuit, and the point is this object can trap photons with energy of 1 over root LC. So let's say I set 1 over root LC to like 4.5 gigahertz. Well, what does this trap look like? Well, I would say it's sort of a harmonic oscillator. It can hold 0 photons or 1 photon or 2 photons. The good news is we've made a nice trap for photons, right? If I make this high enough Q, the photons can live in the trap for a long time. The bad news is the photons in this trap aren't really interacting with each other. So who has studied the Bose-Hubbard model? Okay, so like 2 of you. That's a start. So the way I want you to think about interactions between these particles is if I try to put 2 electrons onto the same ion in a crystal, I pay a large Coulomb repulsion energy between those electrons. And so the entanglement between the electrons comes from the fact that when they try to get close together, they can't because of that Coulomb repulsion. So I would like to mimic that for photons. And so I would like to either have an attractive energy or a repulsive energy when I put 2 photons into the same lattice site. So how should that manifest here? Well, it should manifest as the energy to put the first photon in should be different from the energy to put the second photon in, right? This should be 4.4 gigahertz or 4.6 gigahertz, or literally anything other than 4.5 gigahertz would be great, right? And the point is an LC oscillator, because it's harmonic, meaning the spacings are identical, is sort of fine-tuned to be the worst possible thing for the particles interacting with each other. But for anyone who's ever made an LC oscillator, what you know is that as you apply a higher and higher voltage to it with your signal generator, right before it gives up the magic smoke, the frequency shifts a little bit. If you haven't experienced your LC oscillator giving up the magic smoke, you should ask your PI before you do it. But yeah, so why does the frequency shift as we apply a higher and higher voltage? Well, the frequency shifts because the thing starts to heat up, the inductor deforms. And so when the inductor deforms, the frequency of that resonator changes. Okay? And so my claim is that's the sort of nonlinearity that we want, at least qualitatively. The photons are interacting with the material. That's changing the frequency and backacting on the photons. The problem is to make that happen with a normal LC circuit that you might make on your electronics bench, you might need 10 to the 10, 10 to the 12 photons, right? Some astronomically large number. And this heat that you're dumping into the circuit is entangling you with the environment and destroying any entanglement that the system might have internally. So we need to be able to see the thing sort of deform, at least that idea, but at many, many fewer photons. Okay, so what we need to do, at least intuitively, is make this inductor as small as possible to make it as sensitive as possible to the number of photons living in it. And it turns out The smallest inductor that we can make sort of physically is called a Josephson junction. Now, I'm a cold atom experimentalist by training. So I'd like to tell you what you need to know moving forward for the rest of this lecture from the perspective of a cold atom person. That's what a Josephson junction looks like. It's two aluminum wires with a oxide layer that just acts as an insulator in between. These are each superconductors. Don't worry about that. What you need to know is that the inductance of this junction depends very sensitively on the current flowing through the junction. Okay? And it depends so strongly that the first photon that you put in might require an energy of 4.5 gigahertz, but then the second photon would only require 4.2 gigahertz. So that's like 300 megahertz of attraction when I just add a second photon to the system. Okay? So what if I want to have a photon be able to tunnel from one of these oscillators to another? Well, it turns out all I need to do is add a capacitor between them. And that's enough to generate tunneling from one oscillator to another. And in fact, by changing the value of this capacitor, I can have any tunneling rate that I want. So in our experiment, we choose about 10 megahertz. And so the parameters you should think of here, putting two photons on the same site gives us about 300 megahertz of attraction. The photons tunnel from site to site at a rate of about 10 megahertz, meaning in about 100 nanoseconds, they can tunnel from one site to another, okay? But the important point is that that's much less than the repulsion, or in this case, attraction energy of the photons to one another. So what that means is that they actually can't hop on top of each other because of this large energy defect to put two onto the same site. So we'll think of our photons as sort of like hardcore particles like marbles or something that really can't hop on top of each other. And the last question you ought to ask is, are any of these things that I'm telling you at all relevant, or do the photons just get absorbed and lost long before I can see any of this stuff happen? How long do the photons live in the system? Well, for us, they live in the neighborhood of 40 microseconds. Now you might say, man, John, 40 microseconds feels like a very short time. And in some sense, it actually is. But compared to the time it takes the photons to hop around, it's a very long time. Okay, so they can tunnel 400 lattice sites. If they're on the same site, they can collide like 12,000 times. And it turns out these numbers are quite similar to what you get for cold atoms trapped in optical lattices, arrays of laser beams. These numbers. Okay, and so the thing that we're going to find that's interesting is that even though these numbers are quite similar, the tools that we have for building many body states are quite different. And so the stories I'm going to tell you about the way that we build the states and the states that we build will be distinct from things that you've heard before. So this is what the actual device looks like. Each one of these objects is one of these anharmonic oscillators called a transmon qubit. Okay, why is it a qubit? Well, because the energy to go from 0 photon to 1 photon is different from 1 photon to 2 photons. So I can use that as a quantum bit because I can drive the transition just between 0 and 1 without accidentally going up to 2. So these are our lattice sites. We have these superconducting cavities that we use to measure the occupancy of the lattice sites. And so we can just measure the frequency of any cavity anytime we want, and that will tell us how many photons there are in the qubit. Okay, and the capacitance is just set by the separation between the sites. The time scale for a single experiment is about 10 microseconds. So this means that we can run in the neighborhood of 100,000 experiments per second, which is super nice for data collection. Okay, so we've got all the ingredients. The question is, how do we make a many-body state? So I've told you that we have like 8 lattice sites, right? How do we build a many-body state in that system? Well, you might say, John, just put some photons into the system and then let them equilibrate. Well, if we wait until they equilibrate, what do we end up with? Well, if you wait, eventually they just go away, right? The equilibrium is nothing in the system. Right? In much the same way, if I just take a lattice of laser beams, the equilibrium state is no atoms in your lattice, right? It's not very interesting, right? And if I just put them in and wait a shorter time, Well, then we get the undergraduates or graduate students probably near the coffee, right? Just kind of running around. So how do we prepare this system near its many-body ground state? So what I'd like you to imagine is that I can make a device that continuously fills itself with one photon whenever it's empty, okay? And I would like to connect that to my system. And it turns out that this is very much like a chemical potential. So imagine this thing fills itself with one photon and my system is empty. Well, it's coupled to the system, that photon can hop into the system, and then this thing, before this photon can hop back, the chemical potential object refills itself. But now this photon can't hop into the system because it would have to have this higher energy to do so. Well, once this photon tunnels over by a site, this one can hop in, and then this refills itself. So that's what we would expect to happen. And this is kind of an irreversible reservoir, right? But the essential point is that I'm stabilizing some many-body state from this end by implementing a chemical potential. So the question is, how the heck do I build this object? So what I need is a lattice site or a transmon qubit that constantly refills itself to one photon. So you might say, why don't you just drive the 0 to 1 transition with microwaves, John? That'll put a photon in. Well, that's true, but once there's a photon in there, that drive will just take the photon back out, right? So that doesn't work. What we need is something fancier. And in fact, if anyone's ever built like a laser from scratch, you know that what we're trying to do is make an inversion in this state. And the way you do that is by exciting yourself up to a higher lying state, and then ensuring that you have a fast decay down into this state. And so the idea is, before I can Rabi flop back down here, I have a fast decay there. And now this laser isn't doing anything anymore. Okay, so for this excitation up to this excited state, I can just shine this laser on, that's fine. But how do I ensure that that doubly excited state decays fast? Well, what I'd like to do is couple this qubit to a lossy resonator. So here's the qubit, and I'm going to couple it to a lossy resonator, an RLC circuit that's tuned to resonance with this transition, but not that transition, right? Because remember, those frequencies are different. And so that's literally just putting an RLC circuit on that same lithographically defined chip. And that object, when I couple them together, forms this chemical potential, this dissipative stabilizer for this many-body system. Okay? And so we now know how to make all the pieces. And what I'm going to show you is temporal filling dynamics. This is each of the 8 sites. They start out empty. We have this stabilizing object at the right edge. Okay? And then we look at the dynamics versus time. And over 1 or 2 microseconds, this thing fills up to 1 photon in each of the lattice sites in just the way we would expect. There's this kind of Lieb-Robinson limited filling front that flies across the system as the system fills. Okay, so to understand this a little better, you might like to ask, what happens if I then take a photon out of that site? Well, if I don't turn this refilling reservoir, this chemical potential on, that hole just runs around the system randomly in a quantum random walk. On the other hand, if I do have that chemical potential on, once the hole gets to this edge of the system, it gets eaten by this refilling object, and the system restabilizes with 1 photon per site. This is how you would stabilize what I would call a solid of photons, or if you prefer, a mod insulator of photons, 1 photon on each lattice site. Now, a reasonable comment that people sometimes make is that solid that you made could equally well be made with a Mancala set and little marbles, right? Or an egg carton and eggs, right? What's quantum about this? Well, at some level, I would say we've demonstrated a technique that can be used to stabilize any incompressible fluid. That is to say, this chemical potential object will inject particles into the system as long as the energy required to add a particle remains relatively constant until we hit a compressibility gap. So anything like a Mott insulator or a fractional quantum Hall state can be well stabilized by this approach. Now, suppose you want to stabilize a state which is incompressible, like a fluid. Suppose I want to look at the ground state of 2 photons in an 8-site system. Well, there the idea is the photons want to expand as much as possible to minimize their kinetic energy, but they really need to avoid being on top of each other. Because remember, the most kinetic energy they could possibly have is like 10 megahertz, right? But if they're ever on top of each other, you pay 300 megahertz of energy. So it's much more important that they avoid each other than that they expand. And so we have some kind of a very strongly entangled state of these photons in that system. How would I prepare that kind of a state? How would I stabilize that kind of a state? This kind of a stabilizer doesn't work because this state is compressible. I can add another particle for only a little bit of energy. You just pay a little bit of kinetic energy to add one more photon to the system. They have to get a little closer together, but it's not like you're paying the interaction energy to add another particle here. So how would I build this kind of state? Well, I'd like to tell you about an adiabatic preparation approach that we leverage to build fluids of light. So let's warm up with a very simple example. I'm going to have the energies of my lattice sites, that is to say their frequencies, be different from one site to the next. They will be different by much less than the interaction energy, but much more than the tunneling energy. Okay? And so then we can ask, what is the lowest energy single particle state? Well, it's going to be a photon localized into this site. What is the second lowest energy single particle state? It would be a photon localized there, third lowest, fourth lowest, fifth, sixth, seventh. Pretty simple, right? Now, you might ask, why am I preparing the highest energy state? Well, it turns out when you couple the sites with capacitors, the tunneling energy is negative. So highest energy and lowest energy are reversed. So in the interest of honesty, I will be talking about the highest energy states, but if you prefer, just reverse highest and lowest energy in your mind. So the point is the highest energy state is just a particle here. So I can pi pulse a photon into this lattice site. But then the neat thing I can do is adiabatically remove this disorder and bring all of the lattice sites into resonance with one another. And after I do that, if I do it slowly enough, the particle should delocalize over the whole system. Because in the absence of this disorder, the lowest or the highest energy single particle state is delocalized over the whole system like that. Okay, and if I want to prepare the second highest energy single particle state of the ordered system, I can compare the second highest energy state of the disordered system, and then adiabatically remove the disorder and end up in that state. And this is powerful because on this side, I know exactly what the eigenstates are, right? It's just a photon in one of the sites of the system. I can prepare that very easily with a microwave pulse that puts a particle in. These states are delocalized, so they're more complicated to prepare. So we do this experimentally. We put a particle into that site, and now we're going to look versus time at our data as we adiabatically remove the disorder. And you can watch as the photon delocalizes over the whole system. And we can repeat this experiment with a particle in the second highest energy state. Oops. You get to watch it again. You can repeat this with a particle in the second highest energy state, and we prepare the second highest energy eigenstate. Works great. The next question you should ask if you're an experimentalist is, you said I have to go slowly. How slowly do I have to go? Well, the practical answer is you have to go slowly enough that you get the state that you want at the end of the experiment, right? But we're going to start to be making more complicated entangled states where we might not know what that looks like, okay? So I'd like to suggest a protocol, which is a little bit more involved, but I think quite interesting, where what I do is I put this particle in, I remove the disorder at some speed, I reintroduce the disorder at that same speed, and I ask, did the particle go back into the same site it started in? Okay? And if it did, I would like to argue that the process was adiabatic, right? And so what you can see is as a function of how fast I do this ramp, well, for the slowest ramps, about a microsecond, I go back to the state that I started in with a probability of near unity. Okay, and in fact, I have that up to about 100 nanoseconds, which is a tunneling time, which kind of makes sense. It takes a tunneling time or a couple of tunneling times to be adiabatic for one particle. And then if I go faster than that, I get this craziness where the particle ends up somewhere else. Now, what if I go really, really fast? This is 3 decades here. If instead of a microsecond, I do it over a nanosecond, it looks like I was adiabatic again. And this is where you have to be a little careful. Here, what's happened is we've gone through all of the many-body gaps diabatically, and then we've gone back through all of the many-body gaps diabatically. And so if you go really, really, really fast, it can look like you were adiabatic again. So you have to be a little bit careful about that, okay? But this is the diagnostic tool that we use throughout to see if we were adiabatic. So this is, I think, quite neat because now we can start to prepare 2-particle many-body states by just putting photons into these 2 lattice sites, which are the 2 highest energy lattice sites, right? And then adiabatically removing the disorder. And the point basically is that if I want to know what's the highest energy 2-particle state, well, it's a particle here and a particle there, right? And then when I remove the disorder, I get the 2-particle state where the particles avoid each other, right? But otherwise delocalize as much as they can. You can call this a Tonks-Girardot gas of 2 particles in 7 sites, okay? And I can do this again for 3 particles or 4 particles. And the beauty of this is that the preparation is just pi-pulsing particles into individual lattice sites and then adiabatically removing the disorder, okay? So this works really nicely. And in fact, we can look versus the separation between the particles that they're kind of correlations. If I detect a particle on site I, the probability that I detect a particle on site J, like how anti-correlated are they in space? And depending on how many particles we put in, we see that with 2 particles, they're sort of anti-correlated. They avoid each other over like half the system. With 3 particles, it's a third of the system. With 4 particles, it's less and less. But if I renormalize by the average density, I get more or less exactly what you expect for a continuum Tonks-Girardot gas. So this just really works beautifully for making these highly correlated states of photons in the lattice. To me, this actually suggests a pretty neat set of experiments that we can do next. Because remember, the way these experiments have worked so far is I pi-pulse a first particle in, right, with a microwave tone on a particular lattice site, and then I pi-pulse a second particle in on whatever the second highest energy lattice site is. And then I pi-pulse this third particle in on whatever the third highest energy lattice site is. And in the disordered limit, I have a particle localized in one site. In the ordered limit, the particle delocalizes and so forth with 2 particles and 3 particles. But the thing that's quite neat here is that I'm adding the particles with these pi pulses. So the natural question that you might ask is, what happens if I replace the left pi pulse with a pi over 2 pulse? Okay, and now I have a situation where in the localized limit, I have a superposition of 2 and 3 particles. And if I just look in the localized limit, well, half the time I have 2 particles and half the time I have 3 particles. And in the delocalized limit, well, I get the average of the 2-particle state and the 3-particle state. You say, well, okay, John, that's great, but like, how do we know that we've made a superposition of those two and that we don't just have one half the time and the other half the time? We need to have just some coherence and 2 particles in the system and 3 particles in the system for this to actually be an interesting state. And I'd like to tell you now about how we can detect coherence between a 2-particle like few-body state and a 3-particle few-body state. So the way we do this experimentally is to take our sort of current preparation scheme and modify it slightly. So what's the current scheme? We put in 2 particles and then we pi over 2 pulse to have a superposition of 0 particles on site L and 1 particle on site L. And then we adiabatically remove our disorder. And we have a superposition of like the n particle state and the n plus 1 particle state. These are the n particle ground state and the n plus 1 particle ground state. And what I've been doing is just measuring in real space at that point, right? I'd like to suggest that instead of that, what we do is we do this first pi over 2 pulse. We remove the disorder. So now we have the superposition of the n and n plus 1 particle states. But instead of now measuring, we wait a little while. And the point is, those 2 states have different energy. And so the point is now, they acquire a phase difference, which is more or less the amount of energy that it cost to add that last particle to the many-body system. Yes? Now what I want to do is adiabatically remove the disorder. And so I should go back to having those first 2 particles every time, and half the time having 0 particles on site L, and the other half the time having 1 particle on site L. But the cool thing is that the phase between these 2 many-body states is now mapped onto the phase between 0 and 1 particles on that one site. And so now I can detect this many-body phase by performing a pi over 2 pulse, a Ramsey experiment, on just that 1 qubit. And depending upon what that phase is, well, if this phase is 0, that second pi over 2 pulse will bring me into the 1 state. If this phase is pi, it'll bring me back to the 0 state. So the warm-up, so this is what this Ramsey sequence looks like. I put the first 2 particles in, I drive a pi over 2 pulse on the 3rd site, I adiabatically remove the disorder, I hold for some amount of time, I adiabatically reintroduce the disorder, I drive a second pi over 2 pulse, and then I literally only measure that site. I don't need to look at any of the other qubits in the system. I can learn about the energy difference between many-body states just in this way. So the warm-up, of course, is making a superposition of 0 particles in the system and 1 particle in the system. And what we see, if we ramp really slowly, if we take a microsecond to remove the disorder, we wait for some amount of time, and then we take a microsecond to reintroduce the disorder, is as a function of this hold time, we accrue a different phase between the 0 photon state and the 1 photon state that results in a different measurement of either 0 or 1 on that single qubit. Okay? And if I Fourier transform this fringe, I get a peak, which tells me about the energy of that single photon state. Yeah, for these qubits, like the LO is much better than than anything else in the system. You might ask, how much is the qubit drifting? And that's another question. We're constantly tracking that. If there's a downside to transmons, it's that they drift around a little bit. Yeah.
Actually, the coherence, you meet that before the source of your signal, right?
Yeah. That's certainly true. And we'll see shortly that the T1 of the qubit is, or T2 of the qubit is maybe not as nice as you'd like. Or maybe it's exactly as nice as you'd like. That's really, I don't know you that well. If we ramp really fast, then this fringe has all kinds of different frequencies in it because we've prepared a superposition of many different single photon states. And so when we Fourier transform, we can see all those different frequencies in the Ramsey fringe. And this is actually quite a fun experiment as I vary this ramp length. Now, this is not the delay time. This is saying for each ramp length, what's the Fourier transform? So if I ramp really slowly, I see one frequency. If I ramp really fast, I get a bunch of different frequencies. And so I can see sort of all of the single particle states when I perform the fast ramp. And when I perform the slow ramp, I just prepare this single lowest energy state. And I can repeat that for a superposition of 1 and 2 particles, or 2 and 3 particles, or 3 and 4, and so forth. Now you might say, why don't I see as many features as I have more particles? Well, the answer is there are sort of, if there were 10 features here, there are 10 squared features there and 10 cubed features there. And so until I'm slow enough that I'm just preparing one of them, I almost don't see anything. Right? But you can see that this actually works quite nicely, and we can prepare these few body states very cleanly. And what I'd like to argue actually is that what I'm measuring here is what people in condensed matter kind of think of as the chemical potential, the energy cost required to add one more particle to the system. Okay, and so I can measure that by just performing these particle number superpositions and seeing how fast the phase accrues. So in practice, what happens is I prepare superpositions of 1 and 2 particles for different system sizes. Okay, and what I see is that as I change the system size, the frequency of that Fourier component moves, which is to say the energy to add a particle changes as I change the system size. And so I can do this both as a function of how many particles I put into the system, which is moving in this direction, and how big the system is, which is in that direction. And I can rescale this as sort of a density, number of particles divided by system size. And that's then a chemical potential as a function of density. And when I do that, I get a curve that looks like this. It costs a little bit of energy, a little more energy to add each particle as my density increases towards 1 particle per site. Because remember, as I approach 1 particle per site, eventually I'm paying the whole tunneling energy because I have to localize the particle onto one site. If I want to add another particle once I have one on each site, well, now I have to pay the energy to put 2 particles on a site, and that's this gap. Okay, and so I can perform these kinds of experiments very beautifully and cleanly using this interferometric technique where I sort of make cat states of few photons. We can perform similar sets of experiments where we use this last lattice site to control the system size rather than to control how many particles there are in the system. So the idea is, if I have this site detuned in energy by 1 interaction energy, then if the site's empty, my other particles can't tunnel into that site. Okay? Whereas if there's a particle in this site, then the other particles can tunnel into the site. So here, with this site empty, my particles can live in 2 sites. But as soon as I put a particle into this site, I have 3 sites available. Now, you might look at this and be like, John, isn't the tunneling a factor of √2 higher then? Well, basically what we end up doing is Floquet modulating to correct that. So if we have any experts in the audience, we can talk about that afterwards. But this works quite beautifully because this lets us directly measure the pressure, which is to say the energy cost to change the system size at fixed particle number by 1 lattice site. Okay? And so again, we make these kinds of measurements versus the number of particles and versus the system size, and we see a pressure that that varies with density. Again, in the way that we expect. So I think this is probably a pretty nice place to leave that piece of the story. I have like another 5 minutes here, right? Or is it another hour and a half? I can't remember what you said. But I do want to point out, you know, rather than talking about making noon states here, I think the good thing to highlight is just the perspective on what it is that we've done here at some level. So we're talking about making materials out of photons, but we have one limit where the particles are really localized, right? Where we can inject them easily, we can perform pi pulses, this kind of stuff. We have another limit where the particles are delocalized and becoming entangled with one another and so forth. So what I'd like to argue is that there's an interesting regime of exploring many-body physics where you have a synthetic quantum material or a real quantum material, and you couple it to a little baby quantum computer, right? As we've sort of done here, and start to perform Ramsey experiments or quantum Fourier transforms or these sorts of things in a NISQ era where we're not error correcting up here, but it suggests totally new types of protocols for building and detecting many body states compared to what at least we had thought about before. So the last thing I wanted to talk about just briefly in the waning hour and a half is, you think about quantum circuits, you say, man, John, this all seems like it works beautifully, perfectly. Well, part of that is really a statement that the students are awesome, right? These experiments are very technically hard for reasons that are quite different from the reasons that cold atoms are technically hard, but they're quite difficult as well. But you might say, could we make a quantum network out of these things? Well, the basic challenge with making a quantum network with microwave photons is that the black body background in the microwave is bad at room temperature, right? And you don't want to have cryogenic tubes running 1,000, well, maybe you do, but I don't want to have cryogenic tubes running 1,000 kilometers across the country. So what we need then is to have our two superconducting quantum information processors, and then we need to have transducer objects that convert these microwave photons into optical photons, where we have much smaller backgrounds, right? And then the optical photon gets transmitted, and then we have some way to convert it back at the other end. So the idea is to build some kind of a transducer, and this transducer is an object that takes a microwave photon, converts it into an optical photon, and it can run in reverse as well. And the basic challenge is to find a material that can live in here and can talk both optical and microwave photons to perform the transduction. So, of course, we have to drive it at the frequency difference between these things because microwave and optical photons are quite different, and we probably need to cool it down because otherwise we're going to get like thermal photons running through this system. So there are all kinds of approaches to this. Without going into too much detail, I'd just like to point out that in some sense, they're all optomechanics, okay? The question is just, is the mechanical object a membrane, or is it an ensemble of electrons, or is it one electron? And so in some sense, I would say the cleanest way to do this is to have your transducer be one electron in an atom. And so that's the approach that we've taken. Have a rubidium atom, it can absorb an optical photon, we excite it up to a Rydberg state, it can emit, in our case, a millimeter wave photon, and then be de-excited down with another laser beam to erase the quantum information. So our apparatus in practice is a optical cavity crossed with a millimeter wave cavity with rubidium atoms inside that undergoes this kind of a process. The key innovations here are a way to have an optical cavity which is mechanically very stable despite being in a cryostat. So I can tell anyone who's interested about how to put spring washers into your cavity to really make the cavity much less mechanically sensitive, to get rid of glue sensitivity, all kinds of stuff. And the other key is to have a millimeter wave cavity that can hold millimeter wave photons, but that optical photons can't leak out of. And there's this crazy fact that Aziza Suleimanzadeh discovered, which is if you take a block of niobium and you drill 3 holes in it, where they intersect, a mode lives, and it can't leak out of the tubes. Basically because the cross-section of the hole is √3 times larger than the diameter of the tube. And what this means is that the photon is too big to fit in the tube and leak out. And so we can get basically Q's limited by materials in this kind of a setup. And then the final upshot here, if you look at our data, we see transduction efficiencies of like 60% with less than 1 photon of black body background. It really works beautifully. So what's the good news? The good news is that we've got world-leading conversion efficiency, the lowest backgrounds. It all works great. The bad news is it fills 3 rooms with optics and electronics. So you had this idea that superconducting circuits were going to solve all of your problems. And then you only need 3 rooms of optics and electronics to convert the photons into optical photons to send around. So I don't actually think this is practical. I think the real solution actually eventually has to be optomechanics or electro-optics, right? But in some sense, this can teach you about the fundamental figures of merit that make the science go. What I would say is if you really want to make a quantum network that uses atoms somewhere, it should be an atomic quantum computer at each end with a transducer in between. And what's that transducer? It's a cavity. I love cavities. So I just want to have one slide, a teaser here. We have a new kind of cavity with a waist of about 800 nanometers, okay, that we can trap 1 atom in. And this cavity has a cooperativity above 1, despite only having a finesse of about 60, because this waist is so small. And so we can see a single atom vacuum Rabi splitting. We can detect a single atom in less than a millisecond. And in fact, by adding even more stuff in addition to this lens to this cavity, we've been able to make an array of about 100 cavities, separated from one another by about 3 microns, each with a cooperativity bigger than 1. And so the game is going to be to put an atom into each of these and combine it with these tweezer arrays. Now, right now we're materials limited. Cooperativities are a little bigger than 1, but not a lot bigger. We'd really like to push the materials a little bit and get these cooperativities up to 10 or 20 or 30. And then we're really cooking with gas. So with that, the most important slide, as you all know, is these are the folks who did the science. Specifically, these folks who led the microwave materials work. This crew is the transduction team. And this photo is so old that the small waist cavity crew isn't even in the photo. So with that, thank you all for your patience.